Hello, everyone. Thanks for coming to the class. Let's start the class today. So far, let's go back to the topics that you have seen so far. We talk about the concept of equilibrium, and we discuss several versions of it: Nash equilibrium, correlated equilibrium, dominant strategies, equilibriums, uh, among several other things. And also, we talk about the price of anarchy, price of stability, and smoothness for games. Such that in equilibrium, you know that how good or how bad the situation in an equilibrium comparing to the optimum solution that a dictator assigns the actions to each people. Now, as I mentioned earlier, another very important concept, game theory, in addition of equilibrium, it is the concept of market clearance or market clearing equilibrium that we talk in this session and the next session. So, what is the market clearing equilibrium? There are in particular two of these that we are talking about. One of this market clearance is the Fisher model. The other one is Debreu model, which is more general than Fisher. And if you see the scribe notes, you can see actually the references to get more about it. Here, first we talk about these two important models, a Fisher model and Debreu models. And then we talk about, some applications of these models. It is actually inspired by the Fisher model and has application, for example, in wireless assignments of laptops to hotspots. That we'll talk next. Good. So let's start with the concept of market clearance. What are the ideas? The ideas is that the people are coming to the market, and here each of these people brings some kinds of goods with them, and they have some utilities for other goods that the other people may have. And we can always put something which is called market clearance prices, such that if everyone selects the best set of items according to his or her utility, then everyone is satisfied, everyone gets the maximum that he or she wants, and all the items are gone. So that's the general idea. And the main idea is this market clearance prices that we are talking today. Good. So let's start with the Fisher model, which is a simpler one. So what is the simpler Fisher model? Good. So in the Fisher model, with linear utilities, there are some generalization, but say if we are talking about the linear utilities, we have the following setting. We have a set B of M buyers that their budget is B1, B2 to Bm. We have a set G of N goods for sale with quantities Q1, Q2 to Qn. So these are the items that you want to sell. Utility of buyer I for good J is the Uij, and the amount of good J bought by buyer I would be Xij. And finally, each buyer has a linear utility, that is the UI, the utility, essentially the payoff, would be over all goods J, Uij times Xij. So that's the meaning of the linear utility case. Good. I want to draw some figures here. So that is actually the one that you may want to take a look at it. So You can think about this one, like this is something that you can see that these are the goods that we have. These are the goods. Q1, these are the amount that we have, Q1 to Qn. And then these are the buyers that they come in the buyer M1 to Mn. And from each of these goods, we have Xij that this person gets. And so from this one, it gets something, then it gets from this one gets something. And then some of this, the Xij times Uij would be U1 or UI in general, that would be the utility for buyer I. And good. And we want to make sure that essentially the supply and demands for each of these items would be equal. Good. Now let's go back to the slides. Let's actually describe now. And good. So that is the setting that we discussed. Now, what is a market equilibrium or market clearance prices? So a market equilibrium or market clearing is the price vector P1 to Pn that we are putting for each good, such that the utility of each buyer UI is maximized within his budget. What's the meaning of that? We have this one that you can always select these prices such that for all i's, we have the Pj times Xij is less than or equal to Bi. And we can actually we can make sure that these are can actually make sure that we are spending all the budget. And in addition, the demand and supply for each good J are equal. What's the meaning of that? It means that we have these things that some of for each of these items, some of the amounts that these people want is equal to Qj. And note that, as I mentioned, all the budgets also spend in this situation, because if some buyer had some leftover of budget, then he would buy some more goods J. And then for that good J, we will have the sum of these things would be greater than Qj. So in some sense, we have indeed equality here. Sum of the Pj Xij is equal to Bi. Because again, if there is some budget remaining, then from this budget, this person can buy a little bit of some more goods. So it means that there are more demands for this good. And so in some sense, this is the exact meaning of the market clearance, that we can put the prices such that for each buyer UI, if we are putting, there are this kind of Xij that they will buy such that it would be equal to they spend all their budget. And at the same time, the demand and supply for each good are equal. So no one wants essentially more and no quantity remains. Here, because of these linear things, we can assume that all the Qj's are equal to 1, because if these Qj's are not equal to 1, you can just scale it. Everything scales because everything is linear, so you can just scale. Now, what is the formal theorem for the Fisher theorem? It says that under the mild assumption that each good has at least one potential buyer. What's the meaning of that? There might mean that these are these goods that we have it here. At least each of these ones, at least one person who has some Uij, which is greater than 0 for a buyer I and good J. So for each of them, at least there should be 1% which is greater than 0. Then there is always this market clearance or equilibrium prices exist. So this is the theorem 1 that we are proving it, and this is for the Fisher theorem. But before that, later we talk about like essentially another type of market clearance, again in a different domain, but it is inspired here. It is not exactly like that, but you will see the details here. We will prove this theorem formally here, but before that I wanted to say a more generalized version of this, namely Arrow-Debreu model as well. Okay, so let's go this for the next one. What is the Arrow-Debreu model with linear utility? So this is a bit more general. Here we have these things. This is called Walrasian or exchange model. So this Arrow-Debreu model, this linear utility. This is another market clearance prices that we can put it, or market equilibrium. So what is that? We have a set B of M agents. That is similar to previous case. We have a set G of N goods for sale. Now, this is the difference. Agent I, so there in the Fisher, each agent, essential agent I, just coming with some budget, and there were some goods that they wanted to sell. Here, we don't have this kind of bipartiteness. We have essentially goods and agents somehow mixed. Here, agent I comes to the market with an initial endowments of goods given by, so it has, like, there are these N goods. So when EI is coming, it has some initial endowments, EI1, EI2 to EIN. Again, utility of buyer I for good J is UIJ, similar as before. Amount of good J bought by buyer I is XIJ, that is similar as before, like for the Fisher model. And then each buyer has a linear utility as well. For each I, the buyer, the utility would be the amount that they bought from good J times UIJ. So that is similar. And here, good. So here we can also, these are because everything is linear here, we can assume, like in the Fisher model, that the amount of each good present is 1, as well as equations are linear, and we can essentially do any scaling because the equations are linear. We can do any scaling that we want. So here, essentially, we say that for all good J, sum of the essentially the amount of item that all of these buyers are bringing is equal to. Again, so we can assume that the amount of each good present is equal to 1. Everything because of linearity. If it is not linear, all prices, everything becomes like essentially a multiplier, does not change that. So what is the difference here, as I mentioned? So in the Fisher, we had the buyers and the goods. Here, no, we have a combination. And here, we want to, again, find a price vector P1 to Pn, such that if, now this is the idea, if agent sells his initial endowment at these prices and buy his optimal bundle, then the market clears. No means that no deficiency or surplus of any good. And again, here we are assuming that like these are the P1 to Pn. Not that, I mean, this person may sell some of his items and buy more from the other items. He may have some initial items from this one. He may buy more from this type of items or good and maybe sell from this one. That's essentially the idea. But the case that if everyone tries to essentially maximize, buys the maximum within the budget, what is their budget? The budget is the total amount that they are selling. If within that they are selling, and then They are buying new things. Everything will be clear. No one wants anything more, and all the goods are gone. It's like a very good equilibrium. These are like the one that have been used a lot in the by people in like economists. But these are like some of the things that we have computer scientists have essentially done is to understand them better, maybe find actually this kind of market uh, clearance prices. Again, economists believe that, okay, we should somehow reach to this market clearance prices by this kind of tatonement process that we will talk about them more next time. But here, of course, in this case, actually, obtaining these prices also will be interesting, like getting a polynomial time. That's the thing that like people in computer science, they have spent essentially a lot of time on this, especially around 2000 or something like this. And of course, after that. Okay, so here I wanted to show something. First, I want to say that Fisher model is indeed a special case of Debreu model. That's the first thing. And the other one, I want to prove the theorem one that I have shown here is that, I mean, how can we get this theorem one essentially? How can we find these prices? And the prices actually, as you will see, these are like the idea is somehow similar to the Nash equilibrium. In some sense, this is kind of not quite Nash, is a different thing, but the ideas of proving such things actually somehow similar. Good. So let's go to the next things. First, I want to say why Fisher model is a special case of Debreu model. So consider this one. So what was the idea? In the Fisher, the people had some kind of budget and they have some goods that they want to sell. Now, here, let's do this one. So we want to say Fisher is a special case of Debreu. Consider this kind of endowment matrix that these people have it. So here we have m plus 1. Here we have m plus 1 buyers, or like an agent. No, these are the so this is like these are the initial m guys, and then one more. Similarly, we have these goods that we talk about it. We had n goods and one more. What is that? This more one? This is money. So in the Fisher, the people are coming with money. Okay, so this is the case. So these are the B1 to BM. Each of them this is the budget that they have. And they don't have any of these other items. Now, there is another agent, M plus 1 guy. This M plus 1 guy, this person comes only, he's the person that brings this Q1, Q2 to Qn that we talk about the different items that they have. And we can assume that Q1 to Qn actually is 1. And this person does not have any money. So this is the endowment thing. Now, what about the utility? The utility would be this. These guys, they have the same utility for this M first agent. They have the same utility for the goods. But these people that they come with the money, they don't have any utility for money. So they want to get rid of their money. And now this other person, the last guy, this person is coming. His person does not have any utility for this n items and has only utility for money. So that's essentially the case that you will see that now in this case, these people are coming. The people who have the budget, the money, they want to get rid of their money. They want to buy essentially the goods. And the person who has the goods, he wants to just get rid of all the goods and get the money. And this is actually the one that shows that Fisher model is indeed a special case of Debreu model. And again, Fisher model is more like bipartite case, maybe cleaner case. Debreu is the one that the people are coming, and there is no particular seller or buyer. Everyone is at the same time, both seller and a buyer. Good. So that's the first thing that we have done it. Now let's go and so that we have seen that. So in some sense, Debreu is the most like more general than Fisher model is one of the important ones. Now let's here, let's go for this. Okay, so what was the theorem again that we wanted to prove? We wanted to prove that under the mild assumption that each good has at least one potential buyer, means that like 1% has a utility greater than 0 for this, market clearing or equilibrium prices always exist. Good. So let's go to this one. First, let's do some assumption. Assume that, we can assume that this Uij and Bi are all rationals. And as all of these equations are linear, we can just essentially scaling everything and assume that all of these are some integers, but maybe large integers. So that's the thing. So we are assuming the Uij and Bi's are all of them are integer. Again, this assumption that we had both of them are belonging to Q rational numbers, and as I mentioned, so if it is the case, because everything is linear, you can always scale everything such that all of them becomes integer. Again, maybe large integer, but these are integers. This is the same for our Debreu as well as for Fisher model. Great. Now let's go to this one. So that is the first assumption. Now, so this is interesting. The approach that we are using, as I mentioned, is similar to the one that we use essentially for non-atomic congestion game. What was the idea there? The idea is that we were considering some kind of convex programming, and we mentioned that equilibrium prices for the non-atomic congestion games actually are the optimal prices for these convex programs. And this kind of finding the convex program is somehow the magic part. It is actually more of a magic here. Here, this is a famous convex program called Heisenberg-Gale convex program. And here we consider this convex program. What is the idea? The idea that just maximizing this for different buyers, UI to the BI. And here, those guys that they have a higher budget, because this is exponential, they are more dominating than others. Good. So this is the UI is the utility of these people to the budget BI. And if the budget is larger, it has a more effect. This is a bit magic, essentially. Coming with this kind of, like if you have this kind of equilibrium problems, coming with the correct convex program that equilibrium prices become optimum prices, here is actually the main tricky part, essentially. But this one, again, Heisenberg-Gale is an important one. We have seen that one for non-atomic congestion game. That was also interesting. But here is another. This is the famous convex program. Okay, so consider this convex program for all buyers, UI to the BI. What is UI? UI is the utility for I's that essentially sums over all goods, sum of the Uij Xij. Another thing that we have here is this one, that we know that for each essentially buyer, sum of Xij's should be actually sum over all buyers. For all good J, sum of the Xij should be less than 1. This is again by scaling, as I mentioned, see that we have from each of these Qi's are equal to 1. So these things that the people are buying should be less than or equal to. Last but not least, we are assuming that also Xij should be greater than 0, because each person, for each buyer I and for each good J, Xij should be greater than 0. And I mentioned this. The second one is said that the sum of the amount that the buyers buy from good J should be at most the amount of it which is 1 by scaling. Now, instead of maximizing this, we can just maximizing the logarithm, this function. So the convex, so here we have this maximization things. Maximizing this, just taking the logarithm of this, log of this. Good. Now, here we need to talk about a convex program. What is a convex program that here we have? generally, here, this is interesting. So this function log, here is indeed a concave, and this double derivative is negative. So, okay, so what's the meaning of this? But if you get minus of a concave function, it becomes convex. Here, so instead of maximizing this, we are minimizing this one, which is the same. This is the one essentially that we have. This becomes a convex function. So this is a convex function. And generally, and so this is, we are trying to minimizing a convex, but things here, we have essentially some kind of linear inequalities. Good. So this is the typical form of a convex program. You can actually do it even this one. You can minimize a convex program. What is convex body? So this, you can also do it more general that. But in general, you can minimize a convex program over a linear inequality, or maximize a concave program over a set of linear inequality. This would be a polytope in this case. But we can do even more than that. If this, like instead of this linear inequalities, it is a polytope, we can have essentially convex body. But here, essentially, this would be enough for us. Good. And just note that here, we have this one, as I mentioned. So here we have written this one. These are just some linear inequalities. So everything is good here. Everything is linear here and good. And this one, as I mentioned, we have just written log, and then instead of log, if we consider, which is a concave, we have done it minus, we became essentially convex, and we have this one. And essentially, I mean, good. So we have a convex function, and so we can optimize that. Now, what is the important thing? So generally, this is the one that we are using essentially a lot. So this is the KKT conditions for convex programs. Here we have a convex program. Convex program is our generalization of linear programming that we talked before in this class, and this is like a super important thing. So for the linear programs, as we discussed for the min-max theorem, actually it is something called min-max theorem or duality, or sometimes called Farkas lemmas. And they are essentially having like an LP and some kind of maximization. We have a dual of it, which is a minimization problem. And we have some conditions essentially called complementary slackness that, that relates the primal and dual variables. I don't want to go through the details here. We will discuss more for linear program actually in the next session, that we talk about the particular applications for wireless networks, and then you will see this one. But anyhow, this KKT conditions is somehow a generalization of the duality theorem, that primal dual and complementary slackness that we have for linear programming. This is actually for convex program. So just a little bit about these KKT conditions. So in general, and KKT condition, these are necessary conditions, both necessary and sufficient conditions for optimality under some certain regularity conditions, which are called constraint qualification. So in general, you have a standard convex program, like this. You want to minimize that, the same thing that I mentioned, convex things. GIX essentially, these are some convex functions in general. Or these are some kind of HIX, these are some affine functions. And as I mentioned, GIX, if you are assuming that everything is linear, we can assume the GIX here is just, in our case, is just linear, but it can be convex in general. And these KKT conditions, essentially, what does it do? It considers some here. This is the way that you are writing the duals. It considers the variable lambda I here, and nu j here. This is a typical thing that we are writing, essentially a dual of an LP. So this, when you do that, you have for each equality or inequality here, we have a new variable in the dual. And then we can write, this is the minimization, we can write essentially a maximization problem. This is, I'm talking about the duality with these new variables that we have done. And if you actually take the dual of here, then we get the variables here. But here, this is actually when you do this is for linear programming. For convex programming, actually, this is a bit more general. We consider the Lagrangian relaxation. Essentially, Lagrangian relaxation is doing this. Consider this f of x plus lambda times gix, so lambda times gix, and nu j times hix. So this is the things. This is the Lagrangian relaxation of this formula. And essentially, we know that the gradient, if it is the optimum solution because the convex optimization, the gradient of this, essentially the derivative of this, must be 0 at the optimal point x star. It means that this essentially gradient should be equal to 0. And then so these are some of the conditions, essentially, this kind of that describes the optimum solution for this convex program. So first, we should have this kind of a stationary that the gradient should be 0. Then we have this kind of primal feasibility. It means that the point x star should satisfy this. This is the definition. Then we have this kind of dual feasibility. The dual feasibility says that the lambda I star should be greater than or equal to 0. And finally, last but not least, this is the one that is the important one, the complementary slackness. And this one, what does it say? It said, this is the one that we are using here in these equations. It says that lambda I gix should be equal to 0. What's the meaning of that? It means that if, so this sum should be, so it means that if gi of x is less than 0, then this lambda I should be 0. And if this lambda I is greater than 0, then the gi of x should be 0. This is exactly the concept of this is exactly the way that we are using essentially generalization of duality here. And this is the one that we are using essentially here. So we have dual feasibility, the same thing as linear programming primal feasibility, and this complementary slackness, as well as this gradient that here this gradient should be 0. And yeah, as you will see here, this KKT in general is a powerful tool for solving and verifying optimality of convex programming, and essentially gives some kind of necessary and sufficient conditions based on these variables x star and nu and lambda, which are the dual variables. Based on that, essentially, so that if you have this property, then this is necessary and sufficient for this x star essentially be an optimum solution. So this is important. This is the most important thing, that for a convex program, if a feasible point x star and multiplier this satisfy KKT condition, then x star is an optimum solution. And this sufficiently property is unique to convex optimization. And for if it is general nonlinear programming, KKT are only necessary. But for convex, this is essentially necessary and sufficient. So again, so we say that this is the necessary and sufficient things, that if we have stable point x star and multiplier lambda star and nu star, that they satisfy KKT condition, then x star is an optimal solution for this convex. Okay, so that's about this one. Now let's go back to our setting again. Okay, now what was the idea? We consider this convex program. Instead of max, we have written take the log and then the maximization of concave conversion that becomes the minimization of a convex function, as we have seen here. Now we can write the KKT conditions. I don't want to go through the details of that. But here, the main things would be this. So you can write that one. This is more automatic, essentially in dual. I mean, you can take some other courses, or you can read more about this, essentially duality, which can be essentially a course about linear programming and more generally convex programming. You can write it down, and it's generally a standard way to write it down. And here, now, what do we do here? So here we talk about this one. The variables that we will have here, we have xij's here. So these are the xij's here. And you can actually, so this is the main variables that we want to talk about, this xij. The dual variables for this is for all j's. So the dual variable would be pj here. So these are like this kind of lambda that we talked about in the previous case. So lambda in some sense would be pj here. And that's the one that we are using here. Now, what can we do here? So if you write this one, essentially the conditions, this kind of KKT conditions, that it's, as if you remember, we discussed that if we have these properties, that this lambda and mu all satisfy these KKT conditions, then X would be the optimum for this convex program. So if you write it down, we have these conditions that we can write it down for this. So the first condition is that for all j, pj should be greater than or equal to 0. This is a typical thing, essentially, that comes from the duality, essentially. Because we have less than or equal pj greater than or equal to 0. If it was equality, then it was just equality. So pj is greater than or equal to 0. The other one that is important is this. So what is that? So here we say that pj, let me write it down here. So we say that pj should be greater than or equal to 0. Now, this is exactly the complementary thing that I mentioned, g times, if you remember here, we had it g of x times lambda. So the same thing here. You say that if pj greater than 0, then this is essentially g, that this was less than or equal to 0 becomes equality. So this g of x was equal to 0, essentially, which means here that the sum of the xij should be equal to 1. So pj greater than or equal to 0, but if pj is greater than 0, then this should be equality. Now, similarly, we can write the other one. This is the other type of, this is one for pj, this is essentially for xij. You can write it down. That it says that the uij over pj should be less than or equal to a sum over all goods uij xij over bi. And if, so this is the case that we should have it, and if xij is greater than 0, this we should have equality. And And so what are the interpretations? So Xij is clear. Pj, this is the main thing. These Pjs are indeed the prices that we obtain. How do we obtain it? We are solving this, essentially this convex program, and we obtain Pjs. And I want to say Pj have this good property that we want. Here, one thing, there are some interpretation. Let's understand better these conditions. First one is that the Uij over Pj, what's the meaning of this? That is the utility for buyer I per unit price of item j. So Uij is the utility for buyer I per unit price of item j. And what about this one? This is the utility that you have per budget for the total budget that you have. What's the meaning of that? It means here, for example, let's say that the utility of buyer I per unit price of item j should be less than or equal to the utility for the whole budget. And if you buy something, then Uij should be over Pj should be equal to this one. We have very similar things when we talk about the non-atomic congestion games. So this was the case, very similar things essentially. There also you could get it essentially from KKT conditions. And it says that if you buy some items, if you have essentially you buy something, in that case, the Uij, the unit price that you will get, it should be exactly equal to the utility per budget. So always this one, it should be, yes, for, this is like, again, like similar to Nash equilibrium in some sense, that we say that whenever this should be, if anything is, if you consider a mixed strategy, which is in the Nash equilibrium, all of these actions there, they should have the essentially same utility as the mixed one. Otherwise, you can just drop this guy. If it is less than that, you can just drop that. Good. So this is like essentially the Nash equilibrium type of things that we have here. Now, let's go there and say how we can get the results out of this. So these are the conditions that we have. Now we want to say that essentially, if we have these prices satisfy market clearance, and if we have a market clearance, then these conditions are satisfied. So, and then we are done. So the first thing is this one. That suppose that we have a market equilibrium. Then we claim that the price vector P should satisfy the above four equations. Right. So here, the equations 1 and 2, what was the equations 1 and 2? One essentially says that the prices should be greater than or equal to 0. That's the price that you want to put it. And then if the price is greater than 0, then these items should be sold out essentially, because this is essentially the utility that you have for this item, and then this item should be gone essentially. What about the other things? Equation 3 here. Equation 3 means that the utility for buyer I per unit price of the good J must be less than or equal to his utility per unit budget. So otherwise, so utility for buyer I per unit price of J must be less than or equal to the his utility per unit budget. If it is not the case, what's the meaning of that? It means that this person, if it is more than that, then this person will bought more of good J. It's just by definition, because this one essentially more. So instead of spending the budget on something which is less valuable to this, why this person just spent to buy more of those items. And we know that if we are in the market clearance, no one wants to buy anything more. So we should have this problem. Finally, this is the thing. So equation 4 here. So that was, we are talking about the equation 3 so far. So this was equation 3. So this is the one that we had it for equation 3 here. That Uij over Pj should be less than that. Again, if the unit price and the utility per this is more, then this person essentially is buying more of those items. And finally, we have this one that if equation 4 is, so we know always should be the case because in market clearance and everything will be clear, it should be always less than or equal to that. And at the same time, this is another thing, is that if you buy something, this inequality should be exactly equality. Because otherwise you should not buy essentially. It says essentially this equation 4 says that buyer I purchasing good J implies that his utility per unit price of good J must be the maximum possible, i.e. equal to his utility per unit budget. And this is essentially because these people try to maximize the things. If it was not the case, this is very similar to essentially again Nash equilibrium that we discussed. That essentially if you have a mixed Nash, the utility for all on the support should be equal. Otherwise, you don't play essentially. Good. So we know that if we have a market clearance, we are satisfying these 4 conditions. So these 4 conditions that we talk about. Now let's also prove the other, that if we have these conditions, if we have these are the prices, that the optimum solution for this also gives us a, so we have proved so far that is the case, that if we have a market clearance, it's the prices that we obtain, then it satisfies these conditions. Now let's do also the other one, that say that the prices that we get, here these are the values that we get P1, P2, 2P, and these are the dual variables essentially for this convex program. They satisfy the above 4 conditions. Okay, so so far some of these conditions are good. So we need to say 2 properties essentially that they have. So here it says one of the things, this 2 is good, so that if price is greater than 0, then sum of the xij should be equal to 1. So that's essentially the one that is useful for us. And the other one said that the price should be greater than or equal to 0. Okay, so we need to show 2 things. We want to say that if I put the price as equal to P1 to Pn for this essentially n items or goods, then all good J will be sold and the budgets all used up. Let's prove that. So first thing, we have this assumption, this technical assumption, that every good has a potential buyer. That is important. What's the meaning of that? It means that for all J's which are belong to, there exists a buyer such that the Uij is greater than or equal to 0. No. Okay. Now let's use some of this equation. So we know that this essentially price vector or these variables satisfy these conditions, KKT conditions. Now we want to get the market clearance up. Good. So let me just do that. Let's go to equation 3 here. Actually, let me just make it a bit smaller. I think that would be better, such that we can see everything. Okay, good. Now, here, equation 3. What does equation 3 says? Equation says that Uij times Pj is less than this. Now, we can just essentially just swap denominator here. We can just simple algebra. We can say that from this one, we can get that Pj, so Pj should be greater than or equal to pi times uij divided by this. Now, because we know that for, as I mentioned, again, we are using this thing. We knew that the uij is greater than 0 at least for one item. It means that the pj, this is positive for sure. If this is positive, because bi was positive, so this is independent of this value, whatever it happens, pj would be greater than 0. Now, I'm using just equation 2 here. What does equation 2 says here? Let's see what does the equation. So equation 2 says that whenever pj is greater than 0, sum of the xij should be equal to 1 over all items. It means that this item, the total amount that they buy should be equal to 1. That is exactly the one that I wanted. This means that all of good j is sold. So all of the goods are. Now, the second one. Now, first, I want to say that we always have these equations. Let me bring this one again. Good. Let's bring this. I want to say that always I have this item for all buyers. Why? BIUIJ over this xij is equal to pj times xj. First note that if xij is equal to 0, then both become 0. So then we have it. If xij's are greater than 0, then we have the equality because of this formula 4. So if xij is equal to 0, both sides become, that's the reason that we are multiplying both by xij. So we know that if xij is equal to 0, then we have that. It both become 0. If it is greater than 0, because of this condition 4, we have this in, so you can essentially cancel out this one, and then this becomes this 4. Good. So we always have this formula 4. So let's see what can we say from this formula 4. Essentially, we are almost. So we have this one. Now, just sum this one over all good j's. So here, sum both sides. Both sides over all j's. And here, all j's. What will happen? So the denominator would be the same here. Here, what do we have? If you do that, then if you are doing this, if we do this one, then bi's would be equal to this y. If you are doing over all j's, what will happen is that then we can bring bi's out of this equation, so we don't have any bi's here. Then this sum and this would be equal, so this would be essentially equal to 1. Then this bj, bi would be equal to sum of j, pj, xij. What's the meaning of that? It means that the budget of this guy is exactly equal to the prices times xij. Prices that we put it for with j times the amount that this person buys from that. It means that all the budgets are used up. So we have the market clearing prices. So this is actually a very nice one. Again, somehow in parallel with the same thing that we have seen for non-atomic congestion games that we have written. We say that the equilibrium, Nash equilibrium there were corresponding to the optimum prices of a convex program. And there we could get essentially price of total anarchy. Here is a bit different things. We say that, again, this is correct. The equilibrium is actually equilibrium market equilibrium prices are indeed the optimum solution of a convex program. In particular, this program that we just discussed here. This is the Eisenberg-Gale convex program, which is actually the famous one, and it has several applications. It may actually appear in several other settings as well. For example, when we talk about the fair division, etc. So similar things appear there. So this is the interesting one. But then we know that the optimum solution to this is equal to this. The market clearance is actually are indeed the solution to this. And so we can formulate our problem as a convex program, which can be also solved in polynomial time, but that is also another thing. So we can solve linear programming in polynomial time. More generally, convex program also can be solved in polynomial time. So we can actually use KKT conditions to get and so when we do that, when we solve this one, we can solve KKT's condition. We can also get we can also solve these dual things. We can get the prices out of this. Essentially, this is kind of primal dual. And again, as we are seeing another example next session. It's just a linear program. This is more general things. So this we can solve this polynomial time algorithm. We can get PJs out of this as well, because these are the duals we can solve. Essentially, this Lagrange relaxation we can solve. And then we show that when we get the PJs from these things, from this convex program, this is the one satisfies that. And also, good. So one other things also I wanted to say here as well. We can actually say that because this is like essentially log is strictly concave. Again, similar to non-atomic selfish routing game, we want to say that if there are more than one equilibrium, then utility of each buyer should be the same. So essentially, this also gives you unique equilibrium prices for us. That's another extra property that actually we can have here. So this is the property C. So here, essentially, this is the theorem that we mentioned. This is actually a bit stronger. See that this set of this kind of equilibrium allocations. So this is essentially the first one that we proved here, but the rest essentially comes almost automatically. Here it says that if each good has a potential buyer that we talked, it means that Uij is greater than 0 for that, then equilibrium exists. Also, the set of equilibrium allocations in convex, these are essentially comes from the fact that a solution to a convex program would be convex essentially. And also the equilibrium utilities and prices will be unique. Essentially, that is another one, the same, very similar thing that we discussed before, but these are more come from this essentially properties of these convex programs. And because this is, as I mentioned, if it is strictly concave, then we know that there's a unique solution. And so these prices in equilibrium would be unique. So not only there is an equilibrium, but there is also a unique equilibrium. That is a very nice thing, essentially. So there's only unique set of prices that we can put. Good. So I think we are done for this part. So again, we discussed this. So just some recap about it. We talk about two important models, Fisher and our Debreu model. And then we talk about the market clearing prices. And as I mentioned, we can write essentially convex programs such that the market clearance becomes the optimum solution there. And this will be essentially unique prices. And also we mentioned that the Fisher model is indeed a special case of Debreu, but sometimes actually Fisher is easier to work with, as we will see again in the next session, that something inspired by the Fisher model can be used in a different setting or wireless networks. And it is actually quite nice. This is the result that we have. And we talk more about this. Great. So this is another type of equilibrium which are super important essentially in both CS and econ. And as I mentioned, because now it is a convex program, actually we can also get it in polynomial time. Great. So that sounds good. So we will continue next session, especially if there is no other questions. Great. Thank you, everyone, and bye.